We're going to talk about resistors in series and parallel and how to combine them, how to figure out what the total resistance is for a given circuit, and for resistors that are in series and in parallel, and how they work. So let's talk about resistors in series. And this is what we did in the activity. We hooked up 3 electric cells, and we put a light bulb here, and a light bulb here, and a light bulb here. Okay, now I'm just going to call this V. This is the voltage gain from the batteries. In this case, the activity we did was 4.5 volts. And this is R1, R2, and R3. Okay, so this is going to have a certain amount of total resistance. That's kind of what we're trying to find here. And these are in series. How do we know they're in series? Because resistors in series have the same current. Okay? And so, I mean, if you look at this, here's my current, I. This current, this flow of charge, has to go through the first, the second, and the third resistor. There is only one conducting path between the resistors. If there's only one conducting path between resistors, those resistors are in series, and therefore they have the same current. Now they're in series with the battery. This is only a series circuit. So the current, I'm going to call this the total current, and this is the total voltage. The total current is equal to the current through the first resistor. It is equal to the current through the second resistor. It is equal to the current through the third resistor. So all of these are equal. All right? Now what about voltage? Let's think about voltage here. If you're here at 0 volts, let's say we start at the bottom of the battery, and boom, what does the battery do? It gives us a total voltage. And all the electricity up here had that, I think it was 4.5 joules of energy per coulomb of charge provided by the battery. Now, it's got to give that up, but it's got to split it up into the 3 different resistors. And this is why those resistors were dimmer, the way those light bulbs were dimmer, is because they had to share this voltage. So they had less voltage, they got less energy, less light. But here's what we know. The total voltage provided by them, see, we went from 0 to 4.5. Now we're going to go from 4.5 back to 0. So if you go V1 plus V2 plus V3, these voltage drops have to add up to the total voltage provided by the battery. So the voltage gain has to equal the voltage drops. So this is true. We also know that Ohm's law is true. The voltage across a resistor is equal to the current through the resistor times its resistance. And so I can now use this as a substitute in here. The total voltage, well, that's equal to the total current times the total resistance of the circuit. Well, that's equal to V1, which is I1R1, right? This is just Ohm's law substitution. I2R2. And this is I3R3. So now, all these currents, though, are the same. So they cancel out. If, we can just say they're all equal to each other, so I can divide both sides of the equation by the current in the circuit. They're all the same, so they cancel out. And this says, hey, the total resistance of this circuit is just equal to R1 plus R2 plus R3. And if I keep adding resistors in series together, if I put a R4, R5, or R6, however many I need, plus dot 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 plus R sub n. You just add them all together. It's very simple. We just add all the resistances together. So this is for resistors in series. You get this basic equation. Now let's put resistors in parallel. And what we did in the activity is this. We put a battery like this. And then we had an aluminum foil strip like this. And then we put one light bulb here. And another light bulb here. And another light bulb here. And we could have kept going. I'm going to say this is the voltage, the total voltage delivered to the circuit by the battery. And then we have R1, R2, and R3. Now think about it. This resistor is, this battery is going to push current into the circuit. And this is the total current. Okay, now, but notice that some of the current is going to go through the first resistor, and some of the currents are going to go through R2, and some of the current's going to go through R3. So the current is going to get split up. This total current, some of it's going to go through here, here, and here to get back to 0. So all of this is at, all of this is at 0 volts. All of this was at 4.5 volts. And that's the point here. What is this saying? Resistors in parallel have the same, what's the same about them? What's the same for this resistor and this resistor and this resistor? Huh? The voltage drop, yeah. We're going to go from 4.5 back down to 0. So, if I put the black lead here and the red lead here, it would read negative 4.5 volts. Now, maybe there might be some slight difference because there is a little bit of resistance in the wires, but for right now, we're just going to ignore that and just deal with the ideal situation. That the total voltage delivered by the battery is equal to the voltage drop experienced by the first, by the second, and by the third resistor. But let's take a look at the total current. Do you see, and everybody pay attention right now, if you've been sleeping, wake up, smell some coffee, and look up here. This current is going to go up here, some of it's going to go here, some of it's going to go here, and some of it's going to go through here. But when I add all three of these currents, it has to add up to my total. Does that make sense? Now, if this is true, then, we have V equals IR. We have Ohm's law. And I can say, well, I is equal to V over R. But that applies to all of these. So I'm going to go over here. I'm going to say the total current is the total voltage divided by the total resistance. But that's equal to V1 over R1. And I2 is equal to the voltage drop for that resistor divided by its resistance. And the same thing is true for the third resistor. But what's going to cancel out? All these voltages are equal. So I can just divide both sides of the equation by the voltage and cancel it out. So I get this equation. 1 over the total voltage is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And I could just keep adding resistors in parallel until whatever. So plus, and so on. Now, one thing to remember, when you use this equation, you're not getting the total resistance. You're getting 1 over the total resistance. So what do you have to do at the end to figure out what the total resistance is? Once you do this, you have to reciprocate the answer. So sometimes I rewrite this, I'm running out of room here, as it's being 1 over R1 plus 1 over R2 plus 1 over R3. And sorry, I had to squeeze that in there. Let me zoom in so you can see it better. This is the equation for resistors in parallel. Okay. So add up the reciprocals and then reciprocate at the end. And that'll tell you what your total resistance is. Now, one thing that you should realize is this. The total resistance increase. Let's say I add another, you don't have to mess up your notes, just watch. What if I add another resistor in here, like an R4? Well, here's what I've done. I haven't changed the voltage, it's still 4.5 volts, but I've given another path for current to flow, which means that the total current has increased. And if I say the total resistance is just how much voltage I need to get 1 amp, it's that ratio of voltage to current. Well, I've increased the current without increasing the voltage. Therefore, the total resistance is less. The more resistors I add in parallel, the less the total resistance is. Okay? Which is just the opposite of a series circuit. If I have a series circuit, the more resistors I add in series, the greater the resistance, the less current will flow. The more resistors I add in parallel, the lower the overall resistance, and therefore the more current will flow. In fact, the total resistance, this answer, the total resistance will always be less than your smallest resistor if they're in parallel. Let me get the whole sheet on here. Okay? So this is, guarantee you're going to see some of this on the AP test. So, and they're going to ask you like multiple choice questions about what's going on with voltage and current and the why of it. If you really understand it, can understand what's going on, you'll be much better off. Any questions before we end this? Okay, we shall end this. That is all. Potato?